Hello, it's Keith here, and this is lesson 3 of the advanced series of my Z80 programming tutorials. Now this is going to be a bit of a different lesson to the recent stuff, because the recent stuff's been all platform specific, but this is even going to be a little bit different to the usual stuff in the advanced series and the regular Z80 tutorials. Now today we're going to look at how to emulate Z80 commands using the GBZ80. Now if you're not familiar with the GBZ80, this is the processor within the Gameboy. However, while it's based on a Z80 processor, in some ways it's missing a lot of functionality, specifically IX and IY registers, the R register, the shadow registers, also commands relating to loading in 2 bytes from a memory address at the same time, and various other commands that mean it's quite seriously limited. So when it comes to converting code, you will find yourself in quite a seriously difficult situation, and I certainly have in the past. When I was trying to write my Grimes Z80, I had to be very limited, but I did a little experiment a little while ago where I tried to port the quite complex program Arcus Tracker to the GBZ80, and this posed a couple of challenges. Firstly, the limitations of the processor, which I've just described very quickly, and also the fact that Arcus Tracker was using self-modifying code, and I wanted the program to run from ROM. So I thought it would be quite interesting to look at some of the procedures I had to do to make it work on a limited system like the GBZ80. And today we're going to look at the processor limitations, and while you could argue this is a Gameboy specific tutorial, I thought it was worth putting it in the advanced series, because even if you have no interest in the Gameboy, it's worth seeing the procedures you can use to mimic Z80 commands, either because you're just curious about more advanced method you can use for using the registers and kind of faking things, but also if you're working on a system like the ZX Spectrum, for example, where you need the IY register, but the IY register is actually used by the firmware. Maybe you want to emulate the IY register so you can port some code from the Amstrad CPC to the Spectrum, or equally the TI 83 has that problem, and even in some cases the Amstrad CPC does use the shadow register to some extent. So I thought it was worth looking at how to do this, because even if you're working on a true Z80, there may be times you want to do this kind of thing. So it's worth having a look at and learning how we can do these things. So firstly, let me explain how I've been using the software. So the trick basically is that I have a CPU compatibility function which I load in an include file, and I either use this Z80 compatibility module or this GBZ80 compatibility module, and basically the Z80 compatibility one defines a set of macros, each of which will map to the native command of the Z80. So you can see this EXDHL just runs the EXDHL command, or this ORYIH just maps to ORYIH. So using these macros, while a bit of a pain to look at maybe, is no less efficient for a true Z80. However, for a GBZ80, these commands don't typically exist, and now we can fake those commands, and it means we can quickly convert a piece of true Z80 code to the GBZ80 using these commands. And if you look at my Arcus Tracker example code here, you'll see that all scattered through it are these GBZ80 commands, and this one will load in H and L from a memory address PLY track to PT, and the reason I'm doing this is you can't usually load in H and L simultaneously from that address. You have to load them separately on the GBZ80 because of its limitations. Not just that, the ElDir command doesn't exist, the shadow registers don't exist either, so there's an awful lot of stuff that I'm having to do to get Arcus Tracker working on the Gameboy. Now let's have a listen to it. I'm going to warn you in advance, it doesn't sound great, and the reason it doesn't sound great is that the Gameboy doesn't have an AY sound chip. So I've written probably what's the world's worst AY sound emulator, and it's now going to play my Chibi Akima's tune. But as I say, I'm not trying to sell this to you as a piece of music playing software. The point I'm making is that a piece of software designed to run from RAM on a Z80 processor is now currently running on from ROM, i.e. all the self-modifying code has been removed, and we'll look at that in a later lesson, and it's also running on a processor that is missing a vast number of the commands that this program relies on to be able to work. So even though the program is no longer got those commands, we're still able to get it to run, as you can hopefully hear. Now let's be honest, it's going to be much slower running with these emulated commands, but the point is it's running. If you need to, you could of course optimize further and make things more native, but as I say, this is just a great example of how you can simulate commands that are missing. And as I've said before, you may want to actually do this just in general usage, just to learn how you can do things that maybe the Z80 doesn't do the way you want to, or maybe you want to emulate another indirect register like IX and IY. Maybe you would want something like an IZ. Well, if you know how you can emulate those commands, it could give you all kinds of ideas for ways to use the Z80 processor that you haven't thought of before with regards to its commands. So anyway, as I say, the Z80 compatibility function is just a literal mapping of the simulated macro to the literal command, and it's just there for compatibility because this will compile onto the Game Boy or the Master System, and the Master System is of course a true Z80 processor. And basically speaking, if we run this on a Master System, we will get full speed. There will be no speed punishment because the macros are mapping to the native commands, and because they're macros, if you don't know, an assembler swaps in the code within the macro. It's not a call or anything, it's an actual translation of the macro to the command contained in that macro. So as I say, this is kind of a win-win. We can run it on the Master System with no speed deficit, and on the Game Boy we can run it even though the Game Boy processor doesn't have the processing abilities to run this code in the strict sense. So what we're going to do today is we're not going to be running any code. We're just going to talk through the GBZ80 script here, and we're going to look at all of the contents, and I'm going to describe the main parts and what tricks I've done to emulate the commands that are missing. Now, first thing I should point out, I'm not standing here claiming that these are the most efficient ways of doing these things. A lot of the times I was writing these, it was I found it quite exciting because I was coming to them thinking, well, I don't even know how to do this, but I'm sure there must be a way. And I kind of generally sat on the first way that I found that would work in emulating the command. I didn't sit here trying to optimize it like crazy, because basically most of these have only ever been used in the Grime Z80 program, and then I did some more work on them to get Arcus Tracker working, but once Arcus Tracker had worked, I basically ignored them again. So I can't claim these are the best, but they will work. And as I say, I'm more suggesting that you look at them as a curiosity to see the kind of weird things you can do with Z80 language, because hopefully you'll think of some new ideas from it. So let's make a start, and we start with quite an interesting command. Now, if you're familiar with the EXSPHL command, what it does is it swaps the top item on the top of the stack with HL. So it takes the item off the stack, puts HL onto the stack, and then puts the item that it took off the stack into HL. So it's a swapping procedure, and it means that no other registers are affected. So how can we do this without that command? So what I've come up with is we obviously need a temporary register to use. So what I'm doing is I'm using DE, and to avoid actually using any extra spare memory, I'm actually pushing that onto the stack. Now, of course, the top of the stack will have now moved, but we can counter that by increasing SP twice. This moves us to the place that the stack was before this push command occurred. Now, if we're going to write the current value of HL, we need to back that up, and we're backing it up into that DE. That's why we pushed that DE. Now that we've backed up the current value of HL, we just pop HL off the stack, which gets the new value of HL. Then we push DE, which is our backed up value of HL. Finally, we return the stack to the state that it was here, and then we pop DE back off the stack. The result, DE is unchanged. HL is now the value that was on the top of the stack, and the value on the top of the stack is the old value of HL. No other registers are affected. So this allows us to do a bit of jiggery with the stack pointer, do a push and a pop, and we've now got that command emulated. Now, exchanging DE and HL, that's very easy. All we do is push both onto the stack and pop them off the stack in the opposite order. So we push HL on, push DE on. Now we pop off HL, which is of course getting the value we pushed with DE, and then we pop DE as well. So again, we've used no temporary memory, and we've managed to do that. The ElDir command, now if you've actually seen the description of what this command does, this is a very straightforward command. It copies 1 byte from HL to DE, it increases HL and DE and decreases BC, but it doesn't ever repeat. So that's what we do here. Very straightforward. ElDir is the same essentially, except for it does repeat. I've done a slightly cheating version here because this isn't the most efficient code I could have used here, but it does work, so there we go. But all it is the same as this, just with a check to see if B and C are 0 yet, and if they're not, it repeats again. very straightforward. The halt command is slightly curious. The Game Boy does have the halt command, but it works differently. I'm told if you disable interrupts and halt on a Game Boy, it will actually continue because the halt command is used as a power saving function and it works slightly differently. Unfortunately, there's a bug in the halt command on the Game Boy and it can skip the command that immediately follows the halt command. So what you will want to do is put a no operation after the halt command just to make sure that if a command is skipped, it's one that doesn't matter. So there we go. Now we come to the use of the IXL register here. Now the IX and IY registers do not exist on the Game Boy. So what I'm doing is I am emulating the registers that are missing by using a few bytes of the Game Boy's internal memory to store the values those registers would hold. So we've got IX and IY here, and you'll notice IX and IXL are pointing to the same place because, of course, if you're using this as a 16-bit number, you're effectively using the 8-bit two parts just in reverse order. So that's why I'm doing that. This is just for clarity. I could have used IXL as the definition of IXL instead. We've also got an R register. I use the R register as a random source, so I wanted to emulate that for Grime Z80. And also we've got some shadow registers defined here as well, because we are going to emulate the shadow registers. One thing I should say is this file is pretty complete. It was complete enough to do the Arcus tracker, but there are some commands missing. But I think by the time you get to the end of this, you'll be able to work out how to do the commands that are possibly missing by yourself, because I think the majority of the toughest commands are done, and it's probably just some of the less used commands that are missing. And of course I'll be adding them if I ever need them, but I've probably covered all the ones I tend to use and the Arcus tracker I converted used. So at the moment it's pretty decent at least. So anyway, the use of IXL and IXH and so on. Well, what I've decided to do here is load HL with the address of the virtual register and do the command, in this case the OR command, to that address. Now I'm pushing and popping HL here so that HL isn't affected after this is executed, and the reason I'm doing it this way is because it doesn't use the accumulator, and because of course the flags are correctly represented. So just by protecting HL, the accumulator will come out of this having this OR command applied to it, and hopefully that's the easiest way of doing these commands. So you can see here we're using the IXL virtual register, and we've got other versions for all the other registers here. Now this is a tricky command. We're going to load A into IY plus an offset, so that you can't do these offset indirect commands on the GBZ80, so we're going to have to fake that too, unfortunately. So well, how are we going to do it? Well, we're going to load HL with the fake registers here. Notice we can't load them simultaneously because that's another limitation of the Game Boy, I believe. So we're having to load them in two parts. We then load that into, so we're loading that into HL. We then load our offset into DE, add the two together. We've been protecting the accumulator all this time, and then we load A into the new HL. Now, of course, this is the IY, this is our offset, and so this is the combination of the two. So hopefully we've now successfully emulated that command here. But one interesting thing you will notice is DE would actually support up to 16 bits. So we've effectively created a version that can take a 16-bit offset rather than an 8-bit one. So a slight quirk there, but there we go. And of course we're pushing HL and DE as well around the outside so that they aren't affected either. So you can see here that we are effectively doing the same, roughly speaking, as the command does, but we're not negatively affecting any of the other registers, because of course Arcus Tracker wouldn't work very well if we started doing that kind of thing. So this is a very similar command, only this time we're loading a value directly in, but basically the same command. This version almost the same again, only this time we're loading in the value from H and we're pushing it into the accumulator here. So you'll notice there's an extra push and pop of the accumulator so that when we get outside of the macro, the accumulator hasn't been affected. And again here just for using L, nothing too interesting there. DJNZ, this of course decreases B and then jumps if non-zero. One thing I have noticed when I was looking at this earlier, this could be JR because DJNZ is effectively a JR, but again, whatever, I've used a JP here. So technically the version I've got here is slightly more functional, but maybe I should have used a JR just to make sure that I wasn't writing GBZ80 code that then didn't work on the real Z80s, but never mind. Now this is my random number generator. It's fairly crude. All it does is use the previous value. It increases the previous value, XORs in a bunch of the registers, does a few bit shifts and stores it back. It works surprisingly well actually, but of course it's not a real amazing random number source, but then again neither was the R register, so I think it suffices. So here are some very basic commands. We're just loading from IYL or IYH into the accumulator, so nothing too amazing here. We're just loading from our memory registers or writing to our memory registers in the case of these. Very straightforward. Here we're doing some comparisons with IYL, IYH, so we're doing the same as with that OR command earlier. We're just loading HL with the address of the fake register and doing a comparison because that will not affect AF, and of course AF will be affected by this command here. So that's a good way of emulating it. And INC commands here, just the same. We're using HL again, not too hard. Decrease commands, exactly the same. Now here, this is a bit of a tricky one. I kind of wondering if there's an easier way of doing this, but this is what I've got so far. So we want to increment the 16-bit number IY. So what we're doing is we're loading IY into DE here and then writing it back. Now remember, we can't load 2 bytes simultaneously from an address, so we're having to do the INC here, and then because HL hasn't changed here, we can then just do 1 dec here to match the 1 INC here when we're writing it back. As I say, I kind of feel there's an easier way of doing that, but this definitely does work, and as I say, it'll do for now, even if it's not the best way of doing it. And then there's a dec one here and another one for IX as well. Subtract with carry. Now I'm cheating here, I'll be honest with you, and the reason for that is I've only ever used subtract with carry to just do a subtract. So I'm actually ignoring the carry here and I'm not doing the carry. So all we're doing is we are negating DE, and we do that by flipping all of the bits in the 2 bytes that make up DE. And then what we're doing is we are inking DE to add 1 to it, and then we add DE to HL, and that's the equivalent of subtracting DE from HL without the carry. So that's a command that the Game Boy is missing, but if you know about hexadecimal negative numbers, the way you convert a positive to a negative is you flip all the bits and add 1, and that's all we're doing there. So pretty straightforward. Another version for HL and BC there. Now these are commands to load from an address to a pair. As I say, this is one of the really annoying commands that the Game Boy cannot do. So all we're doing is we're doing it in 2 parts, using HL as a temporary address. So yeah, it's doable, but it's annoying. But there we go. So various versions here. And then here's the opposite, writing to an address. So again, we can't write B and C to an address in one go. So we're having to do it in 2 parts. We're using HL as a temporary buffer. As I've already said, just to reiterate, I fully accept that these are using huge amounts of memory because, you know, we're replacing 1 command with 10 in some cases or more. If memory was a problem for you, what you could do is use calls. So you could have all of these in a common functions module, and then you could put a call to some of these commands, but of course in some cases that wouldn't work. Some of these commands are using the stack, so calling out would actually affect the way that the command should work, but in a lot of cases you could do it. I'm not doing this for saving of memory. I'm not really even doing it for saving of speed. It was just about getting the game working in the case of Grime Z80. And one thing you've got to remember with Grime Z80 is the Game Boy version was actually far faster than the other versions because it had a small screen and hardware graphics. The Amstrad CPC, you know, it may have a proper Z80 processor, but having an IX and an IY register is not going to compete with the fact that the Game Boy has a hardware graphics display and a hardware tile map. So the Game Boy wins even if its processor is inferior. So, you know, as I say, it was more about just getting the game working in that case. So again, just saving IX to a address here, doing it in 2 parts, reading from the 2 virtual registers and saving to the address and the address plus 1. Of course, remembering this is reverse endian, so the small byte comes first. Now by this point you're probably working out how we're doing things, but here we're loading a value into IX and we are loading it into HL, and then we are setting the 2 parts separately. Now I think you could do this more efficiently on some assemblers. Some assemblers have commands to get the low part and the high part of a word. In this case I was probably playing it a little bit safe, because some cases you can do things like remainder division to do it and things. I felt that probably wasn't very compatible with the various assemblers out there, so I thought it was probably safer to just use HL and not have to convert the 16-bit value to an 8-bit value, because I know that varies with regards to how different assemblers will work with things. So anyway, probably playing it a little bit safer than necessary there. And here, just loading a value into IX here and IY, not very difficult. So here again, we're just loading various fake registers, IXL into B and things, nothing too complicated. Just using the accumulator as a bridging method there. And here we're going the other way, storing from registers into IXL, IXH, and so on and so forth. Now this is a curious one. The Gameboy Z80 is almost in all cases inferior to the Z80. However, it does have one quite curious addition that it has, and that is a command to swap the top and high nibbles of a register or even a memory address. So we have this swap command that will do that, and so I thought it'd be a real shame to overlook this quite nice command. So what I've actually done is I've actually done the opposite here, and what I've done is I've made equivalents of the Gameboy swap command, which is 4 RRCAs to shift all of the bits 1 to the right 4 times, which effectively swaps the nibbles. So as I say, the Gameboy, seeing as it had this nice command, it seemed only fair to take advantage of it. And so in this case I did the opposite and emulated the Gameboy's command on the Z80. So now we're getting a little bit serious, and this is where we're going to be swapping into the shadow registers. Of course, the GBZ80 doesn't have shadow registers, so we're using memory for shadow registers. So the first thing we want to do is we want to put AF into another register, and of course there's no real command to shift the flags into another register, so we just push AF and then pop into DE. So now D is our accumulator and E is our flags. Now we load in the shadow values that we currently have from the memory addresses we're using to fake those, and we load those into BC. We then save D and E into those shadow values, which is of course the ones we backed up here. Then we do the opposite. We push BC, pop AF, which gets these values that were in the shadow registers back into the real accumulator, and then we've pushed and popped BC and DE, so those are unaffected by all of our messing here. So this is a rather long but fairly effective way of simulating the AF shadow register swapping command. And then here even more painful and long, and I did actually in my emulated Arcus tracker, this kind of did feel like, you know, the line of over the top. So what I did here is I created a call to this command so that rather than having this command over and over again, I would just have it once and call to it. But again, even on the Z80, I wasn't using that call. I was just using the native command here. So as I say, this is a time that I felt, well, you know, I need this command to get Arcus Tracker working, but this is really beyond the pale, and I think we'll just call to this and you have only that massive command once. But basically the procedure is the same as the one I've just described. So what we're doing is we're using a pair of registers to back up the current value of the register, taking the current fake shadow values of those registers into the true registers, and then saving the copied version of the original value of those registers back into the shadow value. So you can see here we're pulling off the shadow HL and then saving the original value of HL back into those shadow values. Then we're doing the same with DE, and you'll notice we're using the B and C registers here to emulate that. So now we then get back the true value of BC and we back up HL, and we do the same using HL to back up BC, and we get those shadow versions of BC and then save the original versions of BC that we had temporarily backed up into HL. So there we go. Now that's all I've done so far for my emulation of GBZ80 commands. I hope that that's enough to get the vast majority of programs working. It's certainly been enough for everything I've needed so far, and I think I've covered all of the major complex commands. So even if there are any that are missing at this stage, it's probably just a case of looking at what I've already done and copying it and just swapping a command here and there to emulate any others that are missing. So as I say, if you're looking to do Gameboy Z80 programming and you're missing commands and you're tearing your hair out because you don't know what to do, maybe it's worth having a look at this and just seeing if you can't use this to convert that code a bit quicker. And if you want to write code that works on the Game Boy and also on a non-Game Boy system, then I'd certainly advise you doing something like this, or even using my code, because of course it's going to be on my website. That using something like this will allow you to not feel like you're being forced to write very restricted code for the Game Boy. You can still write your very advanced code for your Amstrad CPC or your Enterprise or whatever system, but then you can still get the game running on the Game Boy, because the Game Boy is a huge platform, and despite its rather frustrating processor in some ways, it is a good platform that is, you know, at least as worth looking at as the Master System or something. So I'd strongly recommend you try to do it, unless it's really a system you have absolutely no interest in. Anyway, that's all for today's lesson. As usual, all the source code you've seen today will be on my website, and of course there's an online documentation of it. So if you want to read rather than watch videos, or if you need a bit more time to think about it, please go and have a look at my website. Anyway, thanks for watching today, and goodbye.